Well, welcome back everyone so far. We'll get going in just a few moments. And it's official, folks. We're now in week 7 of 16 weeks, getting through it for sure. We're nearly done with the section 3.4 on the product rule and quotient rule. Here are those two rules down below. And the next rule, the chain rule in section 3.5, this rounds out most of the derivatives that we're looking for in chapter 3. Section 3.6 is going to be an application section on exponential growth, exponential decay. And section 3.7 will be taking derivatives of logarithmic functions. So nearly there. Chapter 3 is about settled. And with what we've got going on so far, next week being midterm week is nothing any too special on that week, but it's kind of pivotal in a way. Once this week is completed out, I'll switch gears on that weekend to filling out the exam 2 information. And whatever topics we complete fully on this week right here is going to be the end of the topics that are going to be on our second exam. Looks like it might go into section 3.7, but I'm not completely certain if we'll finish that 3.7. That one is kind of not quite on the list here, but we'll know officially once we get through this week here. Then next week, we have to keep going forward so we don't get too far behind in the schedule. But we'll pretty much be repeating everything we did relative to exam 1. So you'll see the same materials posted up here, just different sections and that kind of stuff. Well, any questions at the moment, folks, with where we're at or where we're going? Okay, well, let's get back into product rule and quotient rule. Quiz number 4 is not quite based off these kinds of things. This was just normal derivatives. But quiz number 5 will probably be based off product rule, quotient rule, potentially a chain rule problem as well, but nothing too major. So here's where we left off in section 3.4. Well, really, we left off right here. We were doing a pretty difficult quotient rule, and then we went off to the weekend right after that. I felt like before we just push through the notes, we should do a big warm-up. Well, a small warm-up, just so that we're kind of refreshed on how all those rules go. So let's do 2 problems. We want to differentiate them. Part A, just a random warm-up exercise is going to be y equals, let's make it 5x cubed e to the x. Product rule is actually kind of hard to come up with a lot of variation here because without that e to the x, we don't have a lot of functions that can really imply a product rule. But for part B, we'll do a quotient rule on this one. And quotient rules show up all the time, more often than product rule, because anything say like this, x plus 1, x cubed minus 1, there's no great way to simplify this. We just have to use quotient rule on this one here. So here's a couple problems we'll give a try. First, on this one, what makes it a product rule is the multiplication between the 2 functions. So multiplication here implies we need to do the product rule process on it, which means we have to think in terms of what's the first factor, what's the second factor. What you could do is associate this way, use the constant multiple rule by essentially leaving 5 factored to the left. Or another valid approach is you could consider this to be your first factor, 5x cubed, e to the x to be your second factor. Each way gives you the right answer. So it's really up to you how you'd like to do that. Let's go with this route, since I feel like this is usually just a little bit more direct. But if you left the 5 factored out on the left, you'll get the same exact answer. So derivative on this one, dy dx, will be equal to, first, just write out the product rule structure. So we set up 2 terms where the factors are multiplied like this, and the prime symbol moves over from the first factor to the second factor when we're on term 1 to term 2. Let me draw that slightly better. After we've written that in, go to the first factor, 5x cubed. It just goes into the first placeholders, and e to the x goes into the remaining placeholders, here and here. At this stage, we just crank out the derivative. So derivative of this one using the ordinary power rule, it's going to be 15x squared. Here we just copy in e to the x, copy in 5x cubed. Derivative of e to the x would be itself. Then at that stage, we're totally done. The things that are still in color coding are just my way of indicating there's a change there. We took a derivative. Things that went to black are just copied directly from the last line. Well, any questions at all, folks, on that first warm-up? Okay, doing it all over again. On this one, we have a quotient rule, only because of that division right there, and the fact it's an actual function divided by an actual function. No constant in the numerator, no constant in the denominator, means quotient rules are our choice for this one. So, as before, it's all about organizing to start. This time we'll think of the numerator function and the denominator function, or just top function, bottom function for short. Take dy dx. And the structure looks almost like this that we laid out here, just two small changes. So I begin by writing out something derivative, multiplying by something you copy, subtracting the quotient rule, the next set of derivatives, move the prime over to the list location, and denominator is going to be the square of some function. So that's how the quotient rule goes. Like before, if you're organizing this kind of way, the top function only goes into two spots, here and here. Then that informs us where everything else goes. The bottom function x cubed minus 1 is here, here, and finally here. Once we calculate that derivative, we're on our way with it. But this is really the major critical step. If you always write out these kind of structures, it's really helpful for just memorizing how it all goes. And sure, there's going to be notes on a real exam. Here are those kinds of notes that you could use as a guide. But the more familiar you are of how it all goes together, the better you're going to be able to calculate with this kind of stuff. So let's do a derivative on this one. This one is a derivative 1, which means you don't really have to copy in anything, but I'll write it in there just as a reminder. We did differentiate. X cubed minus 1 minus x minus 1. Then it multiplies the next derivative. This one's more involved. The x cubed there becomes 3x squared. The minus 1 goes to a 0. And the denominator is now just x cubed minus 1 squared. At this stage, we did it, folks. That's the whole rundown of that derivative. This simplifies a little bit on the right-hand side. So let's take an extra step and actually simplify all this stuff out. I think we need a new page, though, so let me scoot this down. Okay, back to finalizing this problem. Here, you could distribute 1 in, or just observe 1 times anything is just that thing. So x cubed minus 1. This one is a little bit more annoying, but you can visualize it this way. This and this both distribute in simultaneously. So here to here, we're multiplying by negative 3x squared to get, let's see here, minus 3x cubed when those both multiply x. Then both of those values, the negative 1 multiplies here, 3x cubed multiplies there. So that's just positive 1 times 3x cubed. So negative 1 multiplies here to get us positive 1. 3x squared multiplies here. It's 1 times 3x squared. Yeah, go ahead. Oh, it was x minus 1 from here to here should have been x plus 1 from here. Yeah, good call on that. So this one right here was a change. Let me highlight that mistake in yellow. That was a weird copy. So x plus 1 goes here and here exactly the same as before, which means plus 1 on that one. Which then means, let's redo that distribution. Thanks for spotting that error on that value. This is a negative x times 3x squared. So now altogether, this is negative 3x cubed. Then another distribution. Here to here is negative 1 times 3x squared, so negative 3x squared. And whole denominator is x cubed minus 1 squared. Okay, that's the distribution on this step. Lastly, there's like terms, the x cubes on this, so we can say altogether, the result for the quotient rule is negative 2x cubed minus 3x squared, then all the way over here, minus 1, whole thing divided by x cubed minus 1 squared. And that's finally our total derivative on this thing right here. It was in a nice simplified form when we started, but differentiating it, it really got more complicated pretty fast. Any questions at all, folks, on either the product rule here or quotient rule below? Okay, it's been a while since we took a look at these, so that's how both of those go. And next is this awesome table. We've been looking into these derivatives pretty much since section 3.3 when we were looking into the differentiation formulas. This will be a part of the handout that's going to be at the very end page on exam 2. And I'll try to get those notes finalized soon so you can take a look at those. We have good stuff here like the derivative of the constant is 0. This is a major one. The power rule gets used a lot. We've probably used it about, I don't know, 70 times so far already if you're really counting. Good exponential formula here. Constant multiple rule, sum rule, and difference rule, but probably this and this are where you'd probably be referring to quite a lot, and maybe this one as well. These are the major parts of the table so far. So we have product rule, quotient rule. And example 3 now stands out as a really weird problem in a certain sense. We have two functions, f and g, but they're unspecified except for two function outputs, f of 3 and g of 3, and two function outputs for the derivative, f prime at 3, g prime at 3. And we want to know what is f divided by g prime at 3. Kind of a weird problem, and also f times g prime at 3. The idea of both of these problems is it's really all just about being forced to come back up here and just directly use these formulas, even when there's no function provided, and doing an evaluation all at once. There's exactly one problem like this on WebAssign, so this is a good place to come back to for just a little bit of help on that. And here's how to visualize this all together. Notice the way I wrote this quotient rule. F divided by g. I didn't say f of x divided by g of x. I'm just focusing on the functions. So this is the pattern, basically, where I'm suppressing the input. If we put in an input, whether it's an x or a 3, it still fills out this pattern. So let's write this out. It'll be f prime at 3, g at 3, minus f of 3, g prime at 3, divided by g at 3 squared. So all I've really done is I've come where the red dot is, wrote this entire equation, but because the input is going to be 3, I just put a at 3 on every single one of those functions that appears here. Does that make sense to folks so far? Awesome. Then once we have that, we have function values going this way, derivatives going this way. So we're just going to plug in the information as we see it based off the table above. So inputting in all those values, we have to be really pretty careful here. F prime at 3 means use this value, so 2, multiplies g at 3, but that's a function value, so 5, minus f at 3 here, we just look up at the table as a negative 4. Next one is g prime at 3, another negative 4. Down in the denominator, when we're squaring the function down below, there's no derivative here. So that means we're squaring that value, g of 3. So 5 goes in that position. And That's pretty much what this problem is all about. Again, it's weird because there is very minimal context. We don't even know the definition of F and G, aside from these output values. But it's all about the structure of the quotient rule. So we wrote it out here, pretty much just copying what we saw above, did the substitutions, and now we just need to crank this all out. So this is 10 plus, oh, hang on, there's 3 negations here, minus, with all those negative signs, 16, divide by 25. So altogether, this is -6 25ths for F divided by G at 3. Any questions at all, folks, on surviving that one there? Okay, again, I think these always need a little bit of a repeat. Whenever we do a weird problem, there's got to be a purpose. And the purpose of doing these problems, they are weird. It's just another look at the product rule, quotient rule. So this one's got to be a product rule. It's F times G. So looking at the structure here by the red dot, just copy in this information, but go F prime at 3, G at 3, and so on. So the derivative of F at 3 times the function G at 3, plus, because it's a product rule, the function F at 3 times the derivative of G at 3. So that's where our information goes. Then next, this is the fun part. We just do a table lookup. F prime at 3 is talking about the derivative, so 2 goes here. G at 3 is a function value, 5, plus F at 3 is another function value, -4. G prime at 3 is a derivative, so another -4 on that one. But honestly, we could have just copied in this numerator, switch one thing from negative to plus, but tracking it through twice is just like an extra check on our work to see if we got the same things both times. This time it's 10 plus 16 for a value of 26 altogether. So that's product rule, just a different way to view it. Well, we did, folks. Those are the warm-ups, and this is doing it again in a weird way, where we're paying attention more to the structure. Any questions at all getting through either one of these? Awesome. Well, we've pretty much wrapped up section 3.4 on product rule, quotient rule. There's a little bit more. It's kind of rude to end a section like this without tying it down to something. And this is the something to tie it down in. We have a lot of applications with biology and such, but our book also offers for folks who are more into things like engineering, physics, and so on. Electrical engineering looks like this is what it's more about. These kind of problems as well. Really, any context, you can come up with a good word problem involving calculus some way, somehow. And the context on this says, the power that a battery supplies to an apparatus, such as a laptop, depends on the internal resistance of the battery. So this is just the context we're working in. It says next, for a battery of voltage V and internal resistance R in ohms, the total power delivered to the apparatus of resistance R is this. So we have an internal resistance on the battery, but it says here, the apparatus, imagine the laptop when they say that, has another resistance, R. So the total power being supplied to your laptop depends on this entire function here. The battery has voltage V, so there's where V squared emerges. Internal resistance R, this is for the battery, is way down here in the denominator, but nowhere else. And the apparatus of the resistance R has R appearing here and here. So there's a lot going on with this kind of problem. And what's troubling with it is it's a function P of what variable? There are 3 constants, or excuse me, 3 different symbols here. 2 of them will be considered constants. One of them has to be the variable that we're dealing with. Well, one way we can really identify the variable is in this right here. This is the big ask of the problem. It would be a question if we formed it as a question. Assuming V, the voltage of the battery, is constant, so we have a really good battery, it's not going to fluctuate a whole bunch. The resistance on the battery ought to be constant or else it's failing. So uppercase v, lowercase r are constants. And when it says calculate dpdr, the r right there is being indicated as the independent variable of the whole problem. So this tells us r is the independent variable. It could have been written as p equals. That's much like when you go y equals and just put down a function, maybe x plus 1. That's how this has been written in. It could have also been written in as p of r equals, and then just copying that whole thing on the right-hand side. This is nice because it's telling you immediately through function notation, the variable p is the dependent variable, r is the independent variable. So it's kind of rude that they gave it to us in this format. It hides it, except Leibniz notation also indicated r being the independent variable. So that helped out as well. And this is also helpful there identifying the constants in the problem. So we have two things to do. We want to calculate the derivative of p. Then once we calculate it, the harder thing, let me highlight this so I don't forget, is to give a practical interpretation using the underlying context. Now, second challenge, if r is the independent variable, r appears in the numerator and denominator, implies this is also a quotient rule problem all at the same time. So we need to hit this with quotient rule. And really, that's the whole challenge of this problem. Problems like these that have a legitimate, interesting context behind them are messy. The symbolisms are kind of strange. If you look really hard on that, there's almost no numbers there, right? There's a power 2 of power 2. The rest of it is just pure context of what v and r are to represent. But we can still differentiate this. We're going to organize. There's a top function and a bottom function. So when we go to calculate dpdr, just hit the quotient rule structure and plug things in as they should go. So dpdr equals, here's the structure to start. And really the major reason we focus on the structure so much is not because quotient rule is so hard. It's more, when you start doing it with underlying contexts, it's great to have a guide on where things should go because the problem is suddenly just a lot more visually messy to work with. So there's our structure. We're putting in v squared r into numerator only, first positions. Then r plus r power 2 goes in everywhere else. Okay, so there it is, all filled in. We still have to take two derivatives. This one and this one. They're not easy derivatives, so we have to be careful as we go to compute them. If we can get those values in, our work is pretty much over for the first part, calculating the derivative dpdr. Because it's a tricky problem when you're working in these kind of contexts, an analogy is really, really helpful for showing just what's going on. We want to differentiate v squared r, but here's the analogy. Consider that function where the red dot is as being just a y equals. Remember, v is a constant. So v squared could just be maybe 5 squared, 25, something like that. Read it right in as either 5 squared or 25, up to you. R is the independent variable. So r is like an x. Now we know how to differentiate these things. We've differentiated them all the time. So we can say y prime. Any volunteers for what the derivative of that whole thing should be? Good call, just 25. That's the slope of that linear equation. So just 25 on that one. With the analogy in place, we're going to view it alongside this actual real problem right here. Now assume y is equal to v squared r. This time r is the independent variable playing the role of x, and y prime, just like x vanishes because it's power 1, r playing the role of x will also vanish when we differentiate. It's power 1 as well. All that's left behind is the constant, 25 on the left. Constant on the right is just v squared. So altogether, this is going to be v squared, nothing else. Does that make sense to folks on what should happen on this part? Okay, if you saw it right away, if you eyeballed this and said to yourself, oh, that's just R, good on you. Sometimes that's really tough. And part of our goal in this problem is just to train our eyes to see that. There's a lot of information to connect. So once we see it, we're in good shape. We can just put here, derivative of that is v squared. Now start copying r plus r squared minus v squared r. And here's the next challenge. We also need to differentiate that one. So let's throw in another analogy. If you're differentiating that, that's kind of weird, but a similar sort of problem could look like this. Y equals, where that r is, always think of the uppercase R. Once we identified it as the independent variable, think of it as being a literal x. Plus some other constant, that's a lowercase r. We indicate that's a constant as well. So let's just put in 3 for lowercase r squared. Now, if you want to differentiate that, it's not in a good format for differentiation whatsoever. The chain rule, the very next section, could help us differentiate it. But even if we were in the chain rule section, best thing to do here is just expand that. So we'll take y equals, boil this out by writing x plus 3 times x plus 3, and you'll get x squared plus 6x plus 9. Once it's fully expanded out, the derivative is immediate. Y prime is, go term by term. Power rule here gives us a 2x. Power rule here gives us a plus 6. The constant vanishes, so it would just be a 2x plus 6. Our answer for this part, let me just highlight temporarily in yellow. This is where we're trying to really differentiate, first through the analogy. Answer is going to look similar, but it's going to involve uppercase r, lowercase r. So now we're back to the tough part of the problem. Y is r plus lowercase r squared. We want to differentiate that. We absolutely need to recall r is the independent variable, so think of it as x. But just like before, we also need to expand that all out. So y would be equal to uppercase r times lowercase r, r plus r times itself would become uppercase r squared. Then uppercase r multiplies lowercase r, so we get plus 2 copies of lowercase r, uppercase r. Then you would take r times r for lowercase r squared. So that's the expansion of everything here. We're basically on this line, so now differentiate y prime. R squared is like differentiating x squared, almost exactly the same, just a change of variables. This would be 2r. This part's a little bit trickier, so visualize the 6 here as being 2r. When we differentiate, x vanishes, and 6 copies down. Over here, when we differentiate, uppercase r vanishes, and the constant, 2 lowercase r copies down. So plus 2r. And last thing that happens, over here, 9 is a constant. Over here, so is r squared. If r is constant, any function of r is also constant. So nothing further to write down. The derivative of this whole thing in yellow is just 2r plus 2 lowercase r. It's hard to say that just right. So 2r plus 2 lowercase r. That fills out the entire numerator. But still, in my view, this derivative is pretty tricky going here to here. Any questions about seeing that, either directly through here or through the analogy? Yeah. Oh, that's okay.
Why is b squared not
This portion right here?
Yeah.
Gotcha. So that b squared right there is much like if we were differentiating, say, how about something a little different, maybe a 3 squared times an x, in other words. So what I've done is, when it said v is constant, I threw in a literal constant that we can definitely see. R is the variable, so I put in an x. And when we differentiate this, all that's left over is just the 3 squared altogether, much like going down here from here. Definitely it's weird to see because when we mix what the role is of these things, it's not clear which one is the independent variable. We sometimes want to apply the power rules to like v itself, right, to get a 2v down here. But that's why the initial analysis of all that information becomes like majorly critical. Without knowing r is the independent variable, you have no chance of getting that derivative just right. But other questions at the moment?
So if we're differentiating B2 as a constant, then that would just go to 0. But if it's B2 with R, then it goes down to B2, right?
Exactly, yeah. So if there was a plus right there, we would have just gotten a 1. The v squared would have gone to a 0. Derivative of r would turn into just a 1 altogether. Other questions at the moment? Okay, now next, our whole denominator doesn't change. That's kind of nice, but we can simplify it. If something squared is being squared, exponents multiply. So this is r plus r to power 4. And at this stage, looks like we have a pretty good derivative here. The numerator is involved and it simplifies. Here's one way to simplify it. Notice there's r plus r here. There's also r plus r here and in the denominator. It cancels in. But let's do a little bit of cleanup right on this one just to visualize it better. B squared, r plus r squared, minus, I'm factoring out a 2, so it's going to emerge way out here next to v squared and r, leaving behind just r plus r. Down below, uppercase r plus lowercase r power 4 is what we've got. And you could cancel right here. I'm going to show the actual step, but here's how you could visualize it. If you're the kind of person that cancels here before factoring, it looks like this visually. That factor is gone. There's 2 factors here, so the new exponent is 1. We were only able to cancel 1 factor, so the new exponent down here is a 3. That's where we would end up on if we just cancel right here, right now. But if we do the standard step of factoring, we get the same answer, we just need an additional step. So here's that additional step. R plus R as a group factors out of this whole thing. So I'm going to take it out of here and out of here. Here it is factored out. Factoring is a form of division. So on this first term, we have v squared times r plus r to power 1, because we only factored out 1 power. Drops that exponent to a 1 now. Over here, this entire thing is eliminated when we factor it out. So just minus 2 v squared r. Denominator is r plus r power 4. Here's where the cancellation, oh, that's too aggressive. Here's where the cancellation happens. That just turns into a 3 on the next step. So we're left with a little bit more algebra, it looks like. I'll distribute the v squared through. V squared r plus v squared little r minus 2v squared r under r plus lowercase r power 3. One last step, I promise. We have like terms here, v squared r minus 2 of them. I'll start by writing in the middle term, v squared lowercase r minus v squared uppercase r divided by r plus lowercase r cubed. So this step, all I've done is combine the like terms, v squared uppercase r minus 2 copies of them, to get negative 1 copy of that. And we finally have it, folks. That's our total derivative from the original expression. A lot of work to get to that point. So if this is the expression for power, and it varies, based off the resistance R for the device, then that's the rate of change of power for any specific value of uppercase R. Well, that's what we want to try to say next, the practical interpretation of that quantity. Any questions whatsoever on just getting the actual derivative out?
On the test, do you want it as simplified as possible?
No, I would say for an exam problem, if you even stopped at this line, that would have been sufficient for me. You've got the whole thing in there in correct form, and all this extra algebra, it does have a purpose, but really its purpose is in chapter 4, where we're going to use that derivative, set it to 0 and solve, and that's going to tell us the maximum power for this kind of configuration. But yeah, again, if you stopped right here and you did all the calculus right, that would always be full credit, especially on an exam where time is limited. Well, let's get that practical interpretation next. Recall what the units are. We have power and resistance of the device. So this gives the rate of change for the power to the device for a specific value of R, the internal resistance of the device itself. So that's what this is saying. And for a different analogy, any derivative you can kind of think of as a sort of speedometer. It's a rate of change. It's telling you how fast the power is fluctuating, either up or down, not based off time, but based off the actual resistance of the device itself. Increase that resistance, we might have that this is a negative value, meaning it's going down. Increase it and it might come out as a positive value, but this just depends on what R itself is set to. It's not the power being delivered to the device, it's how the power is fluctuating. The actual power being delivered to the device is the original expression right up here. So any kind of interpretation has to really highlight where you say rate of change for the power, not the actual power itself. But any questions at all, folks, on running through this full problem here? Okay, again, the purpose to all this is not as much at getting the derivative, it's more about if you had specific values for maybe v, lowercase r, you might be able to plot this function. Let's do just that. Y would be equal to, let's put in, for v, just a 5, call it squared. In place of r, I'm just going to put in an x so Desmos doesn't get mad at me. For this r, I'll put in another x plus, this is the resistance of the battery. I'll just put in a 1. I guess I'll put in a 2. Square it. Now we have a graph that looks like this. And it tells us power is maximized when the internal resistance is 2. We can find that through calculus as well. But really, this problem is way more general than that. This is just a structure for any kind of configuration like what's being described. And the manufacturers want to fine-tune things. They want to fine-tune the internal resistance of the battery, the resistance of the device, say the laptop. And so they need this expression so they can change around the values of V and R and still say, what is the maximum value of power as where it's a function of this R right here. We can't graph this at all because it depends on so many more constants. In other words, putting a V here, putting a, oh, that was fine, putting an R here doesn't really help us out because now we have a pretty complicated problem that goes like this. For various values of R, for various values of V, what is the maximum? It's a huge, large problem. So that's why we differentiate this in its fully abstract form to get that expression. This is, again, kind of a preview to what we're getting into chapter 4. We'll differentiate things like these, come up with either maximums or minimums. It takes a lot of work to get there, and this analogy, seeing how to do this derivative and that derivative, in my view, it's the hardest part. So we'll practice it quite a lot. But I think this is a good time to save the notes, move over to the next section, 3.5. Any questions at the moment so far? Okay, let's change gears here. 3.5 is pretty similar in organization to what we just did here in the section 3.4. Because we're dealing with the chain rule, and sometimes this is viewed as the trickiest differentiation formula in a calculus class, we'll go through a little bit of an analogy here just to help us visualize what the chain rule is saying. Then, just like the other problems, sometimes you definitely need the chain rule. Other times, like this one, not a good idea to use the chain rule here at all. So we'll show how that goes. And by the way, this is the chain rule, kind of a weird expression. We'll practice it in this weird abstract way, then we'll just take loads of derivatives. And finally, the application for this section is going to be about the rate of speed of blood flow as it is related to the constriction or the dilation of an artery. So pretty immediate and interesting application on this one. We can't do this application in the very last section. That's a surprise. This is absolutely a chain rule problem out of nowhere. Part of our goal is to say why, what's different about this application versus the power application we were just looking into. But for all that, we've got to understand the chain rule. So here's a simple analogy to get us started thinking in those terms. So imagine this weird scenario where you're watching this play out. A car goes twice as fast as a person on a bike. So imagine a small, slow car. Person on the bike is going really fast, maybe an athlete. This whole expression is really talking about a derivative because there's a rate of speed in there. Right when they said as fast, they're talking about their speeds. Those are rates of change. So now this is really a derivative problem. This whole statement can be re-expressed by the rate of change of the speed with respect to the bike is 2, because the car goes twice as fast as the person on the bike. So we can restate it all in this way. Then there's another level to this. What about the person on bike and a person on foot? A person on a bike, or thinking the same person, goes 3 times as fast as the person on foot. So we say it this way, rate of change with the person on the bike with respect to the person on the foot is 3. So there's an extra level here, but the overall question is, how much faster is a person in a car than a person on foot? So we're comparing someone with a rate of change with a car all the way down to someone with a rate of change of their speed for being on foot. Kind of strange in a certain sense, but we can make a guess on this. If the car went twice as fast as the person on the bike, and the bike went 3 times as fast as the person on foot, anyone see how much fast the person was going in the car than the person on foot? Any volunteers to hazard a guess? 6 times as fast, absolutely. We just multiply the rates of speed. And that's the fundamental idea with the chain rule. Rates multiply in this kind of configuration. Another thing to notice here is that there's a kind of function composition. There's a function relating car to bike, bike to foot, but car down to foot is also being related through. So we're dealing with function composition essentially each time we're dealing with a chain rule. So let's answer this question right here. First, let me fix that. I thought I did. There we go. The answer to this is just like you said, fix that, 6 times as fast. And then it's done. But here's another way to visualize all of this. The rate of change of the person on car with respect to the rate of change of the person on foot can also be expressed this way. We want to do this derivative. First, let's just say what we know. We can say the derivative can be expressed by taking this one here. Oh, forgot how to spell car. There we go. Then multiply by this one right here. And notice how satisfying this looks in a way. This is an analogy. This is not totally correct, but it's a nice analogy for the chain rule at least. It's like ordinary fractions, right? If we thought of them as ordinary fractions, those cancel out. The left-hand side is saying the same thing as the right-hand side. That's just an analogy. The reason it's not fully accurate, but it's still a helpful analogy, is recall if you say dy dx, this is not a fraction. This is just the derivative in Leibniz notation. So what it really is, we take y equals f of x. It's the limit h goes to 0, f of x plus h minus f of x, all divided by h. So these aren't fractions at all, but the analogy is still a powerful one for us to see how the chain rule gets reassembled altogether. Then it's just a matter of substitutions. This rate of change is a 2 you can look up. This rate of change from bike to foot is the 3. And so no matter how we think about it, intuitively the rate should multiply, or this is the literal chain rule in Leibniz notation, rates still multiply, and we get 6 times as fast either way we look at it. But again, the takeaway for this is chain rule is all about multiplying your derivatives together, and there is a third function that you're dealing with. So there's a function composition, or second function is a better way to say this. There's a function composition in the middle somewhere. Well, any questions, folks, with this kind of a warm-up problem here, just understanding what's going on behind the hood in the chain rule? Okay, let's take a look at the chain rule itself then next. The statement of the chain rule feels abstract, but let's break it down. We have to have two functions here. They're both differentiable, but in particular, we want g to be differentiable at the x variable so that f is differentiable at g of x. And the reason we're doing that is the function we want to work with is a function composition. So here it is. Uppercase f is lowercase f composed with g. This is just the name of the function composition. It's not how you actually compute through it. So that's why we say f of g is defined to be f with input g of x. We just said g is differentiable at x, so that part right there by the red dot is differentiable. We also said f is differentiable at g of x, so this whole thing is now differentiable in that case. And if that's true, the derivative of f is this product. And it must be a product because of the analogy we were looking at up there in the notes. The chain rule is a type of multiplication. But this is really kind of tricky in a certain sense. Let's organize just a little bit further. This is common organization we're going to see each time we apply the chain rule. This right here is what I'll indicate as 2 for derivative 2 we take, and we call it the inner function. It's the inner function in that function composition there. It's what's going inside something else. F, we'll call this, after I get the arrow a little bit longer, F, we're going to call this 1, as in it's the first derivative we take. This is the outer function. So in a problem, when we indicate what's inner and what's outer, we can now assemble the whole derivative in this sort of way. Visually, this is what it looks like. I'm going to use green for the inner function. So there it is. And over here, it's copied. That's honestly kind of a surprise. Assembling the chain rule just right takes a little bit of practice because it's copied there, but over here, actually, let me change my color coding. I'm going to say it this way, copied without any color coding, no change with the derivative. Over here, though, we differentiate g. So that's the second derivative we take. Now this one in blue, the outer function, gets differentiated right here. I'll just write diff for differentiate since I ran out of space here. So differentiate f. So you take one derivative for f, plug in g, completely unadulterated, just copy it in, then multiply by the derivative of g, and that's the chain rule expressed in Newton's prime notation. Let's give this a try. Let's save this one for last since we're just thinking about the chain rule right here. Let's apply it to this one in this location. First step, I don't like the way the function's written out, so let's just change the notation. Let's rewrite this as x plus 1 to power 1/2. That gets us started. After we've done that, looking at all this right here, what would you say is the inner function? Is it the power 1/2 function, or is it the x plus 1 linear function? Anyone spot which one should be considered as the innermost function? Absolutely. And visually, it's the function that's inside the other function, so that's a great way to think about it. X plus 1 in this problem is the inner function. So 2 means I do that derivative second. That's what's being indicated here. And I'll call that inner. This one, I'll call this derivative 1 because we do that first in the chain rule, and that's the outer. And I don't know if my color coding is going to combine here. Well, sort of. So there's the organization. Actually, that's kind of hard to look at. I'll leave it just black on this one, and then we'll go back to the color coding on the next problems. Now, finally, we're ready to differentiate. I'll call this one just ordinary y prime. And next, follow the order here. When we indicate something as an outer function, we put 1 next to outer to say that gets differentiated first. Reading left to right, that's where the derivative occurs. And over here, if you differentiate that one first, you're just doing the ordinary power rule. This is what it looks like. 1/2. The new power is going to be 1/2 minus 1. So negative 1/2. And all I've done here is do derivative 1, the outer function. The outer function is the square rooting function or the power 1/2 function. And we just use the power rule on that. There it is. That's what is being playing the role of f prime here, and now it's completely done. There's more to the story. Next thing you want to do is move over a line, go times, throw in a new placeholder, and put a prime on there, definitely as a reminder, you have one more derivative to do. We're multiplying by a derivative, just like over here, we're multiplying by g prime. And this is where the inner function is involved. It's tricky though. Recall, it's copied into the first placeholder. That's this blank we put in, so x plus 1. In the second placeholder, this is where we do derivative 2. And that's why we indicated a 2 here. That's the one we do on the second line. X plus 1 goes into that location. And you know, that's not a bad derivative, right? The derivative of x plus 1 is exactly 1. So on this problem, it cancels off. The whole expression is then y equals 1/2 x plus 1 to power negative 1/2. And you can do a whole bunch of exponent work on this. You can drop that x plus 1 to a denominator. It could be 1/2 root x plus 1. But leaving it in that line is valid as well. We did it, folks. That's our first bona fide chain rule problem. They are tricky. I'm going to try to go slow in this section, indicating these strategies of finding the functions, saying what the order is, and I'll do this structure each and every time we run through the chain rule. Chain rule is weird because the form it takes, the way it looks, is totally dependent on the function you're dealing with. So if it's a rooting function, it always looks like this. But if it's an exponential function, it looks completely different. If it's a logarithmic function, it looks completely different as well. So we have to go pretty careful when we're dealing with these kind of chain rule issues. The caution here is also, just like in the last section, a reminder, just because you can use a chain rule doesn't mean you should. And this is a situation where you really don't want to use it. Here's the reason why. Sure, there's an outer function, just like before, the square rooting function. The inner function is x cubed. But the difference between the two is 2 terms on this one means there's no way to simplify this. 1 term on this one means exponent laws do simplify it. This is nothing but x cubed to the power of 1/2. These exponents multiply, so it's going to be 3 times 1/2, or x power 3/2. With that quick algebra right here, we've eliminated the chain rule once and for all in this problem. And we can just say y prime, use the power rule. 3/2 comes down as a coefficient. New power next is 1 less than 3/2, so we're subtracting 2/2 to get 1/2 altogether. And the whole problem stops right at that step. If it was x cubed plus 1, it's a radically different problem. I can't do that simplification whatsoever. It's really just chain rule altogether. So spotting the difference is a really big, important goal in this class, because notice how much extra work you have to do if you use the strongest method on every single problem. It's kind of strange, but if you look for just a routine way to solve these problems, oftentimes that is the best way to solve them. It doesn't always work, so we're going to practice chain rule a whole bunch more on the next set of problems. But any questions at all, folks, on looking at either versions here? Okay, so let's try out the next problem then. This is another one of those weird problems where there's no context. All I have is a function composition. Uppercase f of x is f composed with g, or f of g of x. Now we have loads of different function values with the goal of evaluate f prime at 0. So that's our whole strategy here. Well, just like before, it's all about knowing the expression in the chain rule, how to put it all together. So if this is your f of x, that would indicate that f right here is derivative 1, outer. G, that function right there, is derivative 2, inner. Our organization through color coding, which will show up this time, it's always going to look like this. So if we go f prime of x, first we differentiate f. They'll look like this. F prime of something. Then we multiply by the derivative of something else. That's the inner function. G prime at something. That something here will just be g prime of x. Over here, g of x itself copies in. To me, that's kind of the thing that's weird about the chain rule, that this one copies, but the other parts you do take derivatives on. So that's f prime of x. That's not what we want, though. I mean, we already had f prime of x right up here, right? What we want is f prime at 0. So we can drop a line and say f prime now at 0 is equal to f prime at g at 0. So I plugged in a 0 here for that x, then go g prime at 0 here as well. Let me fix a bit of my penmanship first. So example 2 is just forcing us to really take a strong look at the formatting of the chain rule up here, and also do an evaluation. A little bit tricky though, because this time, not all of the data that's provided here is actually relevant. Some of this data is going to mess us up if we plug it in the wrong order, for example. Very first thing I would want is g of 0. Here it is. No, it isn't. Let me try again. G at 0 is 8, so we can plug that in. And we can also just grab our g prime at 0. That's the 4 from right here. So this is going to turn into f prime at g at 0 through the color coding. We see that one's an 8. G prime at 0, we can substitute in just a 4. And now we need another evaluation. Notice f of 0 equals 3. I mean, it's correct. That's what they are saying the function does. But it's totally irrelevant to us. That doesn't help us out at all. If we use that, we probably are going to get the wrong expression. Because what we really want is f prime at 8. F prime at 8 is -2. So this whole thing becomes -2 multiplied by 4 for -8 altogether. So kind of a weird problem. We didn't even know the original functions, lowercase f, lowercase g, just some extraneous information about it. But for those three values right there, we can determine f prime at 0, where f is the big composition of those functions. Well, any questions at all, folks, on doing it, I guess, a third time this way?
I have a question for, we're supposed to evaluate f derivative of 0, but highlighted in blue for the derivative of f is 8 in the parentheses. So would we still use that? Up above.
Gotcha. So
Question is everything for now.
for this one value right here, yeah, we plugged in f prime of 8 as a -2. And I see what you're saying. We're supposed to calculate f prime at 0, right? It seemed like there's a bit of a conflict right there. But the f prime of 0 happened right over here. And all we had to do is plug a 0 into those two spots right here. So we would put in a g of 0. There's the g of 0 in that position. Then we had to throw in a g prime at 0. So there's g prime at 0 at that position there. So for this line right here, in this equation, we are now officially calculating f prime at 0 when we plug in 0 in those spots. Does that make sense with that step right there?
Yeah, sorry. I just didn't get that that when we solved it all the way through, that f derivative of 8, it gave us that in the equation, so it gave us what we needed. Sorry. Yes, it does. Thank you.
Way, yeah. What was tricky with that next step, though, going over here on this one, was I think when this problem was written down, I think I copied this verbatim out of our own textbook. There was a check to see if we put in a 3 there. And it makes sense, right? If it says f prime of 0, it almost feels like you need a lowercase f prime of 0 right here. But really what we had to do was grab the g of 0 value, plug in the 8. So that's why that went in that location there on that line. So that's the connection of why there's an 8 on that f prime, despite the original underlying question being do uppercase f prime at 0 itself. Does that help to see it a little bit better that way?
Yeah, thank you.
Yeah, absolutely. Yeah, go ahead.
Yeah, 2 for F prime, and then I got 8 times 4. Where did I go wrong there?
So you said you had a -2 for that spot right here?
Yeah, but -2 for F prime, and then GO, I did 8, and then G prime, I did 4. So I had -2 times 8 times.
Let me track through that once again. So from this position here, you had f prime at what value?
Negative.
Gotcha. So -2 would go inside there. Oh, hang on.
Times 8.
Well, sorry, question over here as well. Oh, I see, yeah. So there is that value 8. There is that value -2, but we have to see that 8 actually vanishes because when we go f prime at, oh, hang on, let me try again. F prime at a +8, the whole g of 0 here just gets wiped out. It's just a full-on substitution. So now when it becomes f prime at 8, f prime at 8 itself just turns into that -2 now. So that factor right there. Yeah, go ahead.
According to G of 0, on that side, that would show.
Let me double check where those are. So parentheses, this one right here. Oh, gotcha. Yeah. Yeah, that makes a lot of sense. This is all targeted to the derivative of f input as well. I do agree with that. That's a great color coding on this one. So when we went over here, just a full swap, g of 0, now 8. And all we're dealing with is f prime. And now, yeah, those color coding makes a lot more sense. That's a tricky thing about color coding is if you're a little weird with it, it can cause more harm than good as well. That's a great change. Does that help to see it that way, differently?
Things get,
Yeah, there's another question or another comment in class that it's basically like order of operations, work way inside, work your way out, and then get your number is essentially what's going on. Or other questions or comments about that one so far? Okay, glad we did this problem. I mean, this really highlights the complications when we're dealing with a chain rule. Lots of weird things happen, and when we go to evaluate at an actual value, f prime at 0, a little bit of extra confusion and complication as well. So either way you can look at this and think about the chain rule is very helpful. Next thing we're going to do is now practice applying the chain rule into just ordinary derivatives. So this is like the bulk of the homework problems next. Here's how it goes. It says calculate the derivative, simplify your answers. But you know, we haven't used the chain rule a whole lot. Let's actually do this as well. So here's our cheat sheet. This is the chain rule essentially. If we can take what's being expressed in this formula using the same strategies we were using above in the notes, and now apply it to problems like these, we're well on our way of understanding just how the chain rule goes. First thing we need to identify is what is the actual inner function inside here? Well, there's two functions. We have the power 103 function, a degree 3 polynomial on the inside. Function on the inside would be the g of x. So this is the inner function. We differentiate second, so 2 inner. The outer function, for which we'll differentiate first, is the power 103 function. So this is function 1, outer. It's function 1 in the sense that we'll do that derivative first. And really, we're dealing with two functions. The outer function is, we rewrote it, y equals x cubed. The inner function, all of that stuff right there in green, just goes inside x cubed. And differentiating y equals x cubed, really fast, right? You just get 3 x squared. Except that x becomes a placeholder for which we plug in all of that stuff. That's what this is saying right here. You're plugging in g of x after you take the first derivative, the 1 for f. So this is how it all comes together. And now we can say f prime of x equals, follow the structure. You do the outer derivative first, so differentiate the 103 power function. Kind of like doing, oh, hang on, what did I do there? Let me fix my little expression. What I was trying to say here is that the outer function is x equals 103. My brain just wasn't accepting that. It's a high degree power function. And if you differentiate that, you get 103 x to the power of 102. Sorry, that's how I was trying to think about on that problem there. Sorry for the distraction on it. But now correcting the analogy over here, differentiate this, and this is what you get. 103. New power is 102. And this is the entire f prime portion of doing the chain rule. What you really want to do immediately after is this one as well, times the derivative of g at x. Actually, let me retune my color coding. I think we left it blank on this one to convey g is just copying in. We kept it green over here to say it copies in, but with a derivative. So whatever your function g is, you take this whole thing, drop it into this stage. 8x cubed plus 9x squared minus 11x plus 6. And if that was just x, and you multiply by the derivative of x, you would just be multiplying by 1. That's why we don't need a chain rule over here. Multiplying by the inner function, which is x, is not making any change at all. You're multiplying by 1. But if it's anything other than x, you do need to multiply by its derivative. So 8x cubed plus 9x squared minus 11x, and let me just extend that a bit, plus 6 gets differentiated right here. That's this portion of the chain rule, and that's why we call it 2. Just a reminder that it'll be the second derivative in a 2-step process. Any questions so far, folks, with this first step? Okay, finalizing this, we have f prime at x equals 103, 8x cubed plus 9x squared minus 11x plus 6 to power 102. And last, just differentiate this one as normal. 3 will multiply the coefficient 8 for 24, x squared. 2 multiplies 9 for 18x. This is linear, so we get just the slope, negative 11. This one's constant, so it goes to 0. And that's our total derivative. We don't have to do anything further to it, so no worries about expanding this out to power 102. The power is ridiculous just to show, even if I can't expand this out, chain rule doesn't care. We can still get a fast derivative in a reasonable way. So that's what we'll be practicing more and more of when we come back on Thursday's class. But any questions at the moment, folks, with getting these down? Yeah. I would say so, yeah, absolutely. It's, let's see here, nothing we could really factor out of that group. This is already in a factorized form. So I think this is the answer that just about everyone would leave it in this format here. Yeah.
That 1 and 2 at some of the smaller. Which is
Yeah, you'd have the opportunity to really actually expand it all out. It'd still take a lot of work, but you'd have an equally valid answer, just a lot more terms. It kind of just depends on what you're going for. Simplified sometimes means as factored as possible, but change the context. Simplified might mean as expanded out as possible. In other words, if we were going to do the opposite of differentiate this, say we're in chapter 5 and we want to integrate this, we don't like this format. We would really want to expand it out if we could, which means this is not a great function to deal with such a high power. But yeah, either form, either expanded or factored in this would be considered just fine. Other contexts will inform us if we really want to change the formats. But other questions at the moment? Okay, well, when we come back on Thursday's class, we'll just do more and more derivatives, see how all of these other things are going to go. Some of them are a little bit more challenging because they're combining, looks like this one is quotient rule and chain rule. This one's product rule and 2 chain rules. But then after we do all that, we're going to do different derivatives of more exponential functions. This is where the chain rule gets a little bit vague and foggy, so we'll spend extra time here as well. But this will be our stopping point for today. If you have any questions, I'll be happy to help out. Otherwise, I'll see you all in Thursday's class. Have a great afternoon, folks.